Okay guys, we're going to start scientific notation, which is lesson 7-2 out of your textbook. Scientific notation is actually something you've learned back in middle school, but we'll put it into the Algebra 1 level of math. A number in scientific notation is written as the product of two factors in the form of a times 10 to the nth, where n is an integer and a has to be greater than or equal to 1 and less than 10. These are actually three examples of scientific notation. One of the ways to think about scientific notation written outside of the technical definition is to remember that 1, it has to be a power of 10, and 2, the number to left of decimal must be a single digit between 1 and 9. So if you look at these examples, this is a power of 10, and the number to the left of the decimal is an 8, which is a single digit 8. Oops, it doesn't want to do that. Anyway, right here, this one is a power of 10, and the number to the left of the decimal is a single digit 4. Power of 10, single digit of 7. If you look at the examples down below, we have to be careful because sometimes numbers look like they are not, or they are written in scientific notation, but actually they're not. For example, if you look at choice A, they want to know if it's written in scientific notation, yes or no. Well, the fact that it has by the power of 10 is good. The problem, though, is that the number to the left of the decimal point is a 0. That's not between the numbers 1 and 9. Therefore, that's not written in scientific notation. Example B says 2.3 times 10 to the power of 7. It is a power of 10, and the number to the left of the decimal point is a 2, which is one of the single digits between 1 and 9. So yes, that is written correctly in scientific notation. In choice C, the power is not by a power of 10, it's by a power of 100, and it has to be a power of 10, so therefore that one is not written in scientific notation. Okay, so be careful. So sometimes they'll make it look like it. A lot of kids think if they see times the power of, like over here, by a power of 10, they automatically assume, oh, it's times 10 to a power, therefore it's scientific notation, which may not be the case. So let's go ahead and do these. The first couple screens are going to be easy, or should be easy for us. They'll bring us back to middle school math. The decimal point in the first one is imaginary. It's right here. The number that they're showing is 678,000 is a very large number. We're going to write it in scientific notation, which means we're going to move our decimal point over far enough where whatever's to the left of the decimal point is a single digit between 1 and 9, which would be right here. So it's 6.78. The 6 is my single digit, and then times 10. Don't count zeros when you put your power. You count movements. 1, 2, 3, 4, 5. The question is it a positive 5 or is it a negative 5? Well, because your original number is larger than 1, quite a bit larger than 1, it's going to be a positive. If this number was smaller than 1, then it would be a negative. Like this one. This one's very small, much smaller than 1, so we know our exponent's going to be a negative. The number to the left of the decimal point is a 0. That's not a single digit between 1 and 9, so we're going to have to move our decimal point. 1, 2, 3, 4, 5. So it's going to be 3.2 times 10, and I moved it 5 places, and because it was small, it's to the negative 5. The next one is big, so we know it's going to be a positive exponent. 1, 2, 3, 4, 5, 6, 7. So it's 5.14 times 10 to the positive 7. This one is a small number, so we know it's going to have a negative exponent. 1, 2, 3, 4, 5, 6, 7. So 7, you don't need to put your decimal point, even though it's, you can just leave it as an imaginary, times 10 to the 1, 2, 3, 4, 5, 6, 7. And it's going to be negative because this number was much smaller than 1. All right, they're going to reverse it on us. They're going to give it to us in scientific notation, and we have to change it back to standard notation. So we're multiplying by a power of 10. 10 to the 7th power means 10 times 10 times 10, 7 times, which means you're multiplying it by a large number. When you take that number and multiply it by 5.23, it's going to make it bigger. So what we're going to do is you're going to have 5.23, and you have to multiply it by a power of 10, which means you're going to go 1, 2, 3, 4, 5, 6, 7. So we end up with 5, 2, 3, and you have 1, 2, 3, 4, 5 empty loops, which means you annex 1, 2, 3, 4, 5. You're not adding, you're actually annexing, which means to attach. (4.6) times 10 to the negative 5th. Because it's a negative, it means it's going to make the number smaller. 1, 2, 3, 4, 5. So we got to go to the left. We have 1, 2, 3, 4 zeros. This is the 0 on the other side. So it's 1, 2, 3, 4, 4, 6. 2.09 times 10 to the negative 4. It's going to make it smaller because it's a negative. So it's going to 1, 2, 3, 4. So we end up with 0.123 empty loops, means 3 zeros, 209. Make sure you guys are putting me on pause, trying it, and then playing. Times 12, that means you got to go 12 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That means you have 38. If you count the empty loops, it's 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. Big number. There it is. All right, let's apply this a little more. Comparing numbers in scientific notation. If you look at the example that they give us up here, they give us 5 numbers. All of them are written in scientific notation, which makes it easier for us to arrange them in order from least to greatest or greatest to least by looking at the powers of 10 first. If you notice these two numbers have the same power. So we know that 10 to the 7th power is smaller than 10 to the 8th power. So this grouping must be before this grouping as long as we're ordering least to greatest. Then you look at the ones that have the same power, and you know 1.41 is smaller than 7.49, so this one must be smaller than this one. Whereas over here, these guys have the same powers of 10, and 1.6 is smaller than 1.8, so that means this guy comes before this guy. What they're going to do, as you see in the example below, which is kind of crammed in there a little bit, we're going to have to change these to scientific notation. There might be a couple in there already done for us, but if they're not, we're going to have to change it back. So if I look at the first one, 49.7 times 10, which really is 497, 49.7 times 10 is not written correctly because there's 2 digits to the left of the decimal. They only went here when really they should have moved it 2 places. So that would be 4.97 times 10 to the second. Times 10 to the second, yeah, so you have to move it over 1 more place. Okay, so that takes care of that one. 4.17 times 10 to the 7th, it's a power of 10, single digit before the decimal. So that means I'm just going to leave it alone because it's written in scientific notation correctly. Third one is 0.047 times 10 to the 9th. That has not been written in scientific notation correctly. If I change this back out, multiply it by a power of 9, That'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. What happened was when they started over here originally and they counted over, they went too far. They really should have stopped here, but they went 2 places too far. So it should have been 4.7, and they went 9 movements. They really should have stopped at 7 movements. So now we have it written correctly in scientific notation. Third one is 495. That's written in standard form. We have to go 1, 2. So it's 4.95 times 10 to the second. Now let's group them. These are both powers of 10 to the second. And these are powers of 10 to the 7th. So we know that the ones that are 10 squared are going to be smaller. Well, 4.95 is smaller than 4.97. So that must mean this one is the smaller, which is the 495. So that's going to be, let me write it down here, 495. That's this one. Okay, can't see that. That's this one. Then we're going to have this one's going to be the next smaller, which is the very first one. Notice how I'm writing them back in the original form. 49.7 times 10 would be this one. Now we're down to the powers of 10 to the 7th. 4.17 is smaller than 4.7. So the third one will be this one, which was written as 4.17 times 10 to the 7th, comma. That takes care of this one. And then the last one, which is the largest, was written as 0.047 times 10 to the 9th, which was this one. So that's my actual answer of the original numbers in order from least to greatest. If you change them over to scientific notation, it will make it easier for you to determine which is the smallest to which is the largest. That's going to be our homework for tomorrow.